Hey, this is Dr. B, and let's take a look at some equilibrium problems. It's those reaction ratios which we're going to see are very important for this. Okay, here's a problem. We've got some iron ions reacting with thiocyanate ions to make a combined ion known as an iron thiocyanate dication. Fine. And we have some initial conditions. The iron 3 plus is 6 molar. The thiocyanate is 10 molar. Mix them together, let them go to equilibrium, and the iron thiocyanate product is 4 molar. I'm going to solve this without doing any sort of bookkeeping, and then we'll show you the bookkeeping method, which we'll call an ICE table for initial change in equilibrium. Well, if this went up to 4 molar and it was initially 0, it went up by 4 molar. Now, since for every one of those that forms, one of those must go away and one of those must go away, I know that this will go down by by 4 molar to 6. This will go down by 4 molar to 2, and the equilibrium expression, which is that over that times that, will be 4 for the iron thiocyanate, 6 for this on the bottom, and 2 for that on the bottom. That's 4 over 12. The answer is going to be a third. That's called doing it in your head. Now that might be a bit too much for seeing this for the first time, so let's lay it out in a nice clean ledger. We call this an ICE table. Write the initial, the change, and the equilibrium. At the top, write your balanced chemical equation, which is given, fine. And what did they say initially? Well, this is 6 molar. That's 10 molar. Unless they tell you the reaction is already partially going, this will always be 0 for the products, right? Nothing's happened yet. They don't tell you the change, but they do tell you that you've got this much product at the end, so write in what you can. Now it's simply a matter of doing the bookkeeping. Well, it went from 0 to 4. I guess it went up by 4. And then the big aha moment is that that must go down by 4, and that must go down by 4. After all, for every one of those that forms, one of each of those go away. And that might lead to you to say, hey, if there's a 2 in there, it's not going to be the same. And you're right. So now just complete your ledger. Plug in, right? Set up your equilibrium. Constant expression, it's products over reactants, coefficients become exponents, but for the first example it's all ones, and it is 4 over 12. This has an equilibrium constant of a third, which is not great. That thing is going to not go very far on its own. Here's another one, but in this case we've got an esterification reaction. Acetic acid and ethanol making acetate and water, and I would just slash that right away. Remember, it emits solids and liquids. I haven't read the problem, but I'd scratch that out. Now they do give you some initial conditions here. It's each, so 0.810 for this and this, fine. They heat it up, they wait till it gets to equilibrium, and one of the reactants, acetic acid, goes down by 0.062 molar. Good, so this goes down by 0.062 molar. Let's do the big important stuff. That's going to go down by 0.062 molar to the exact same value. And this will go up by 0.062 molar. And since it was at 0, that's going to be its number. So I think the numbers will be 0.062 divided by 0.748 squared. I could solve it right now, and that would be fast. But let's do a nice clean ICE table. Here's our balanced chemical equation. We are omitting water. It's omit solids and liquids. Those two are given, and nothing's happened initially. This goes down to 0.748, the acetic acid, so now we're in a position to say that went down by 0.062, as will the ethanol, and the ethyl acetate, 1:1:1 ratio, will go up by 0.062. Sometimes students have to struggle initially to recognize that reactants always lose something. Products always are gaining something. And completing our ledger and plugging in, nothing gets squared. We did omit the water. Gives us an equilibrium constant of 0.111, which is even worse. Example number 3. We got a tank of hydrogen sulfide, which smells horrible. It's at 10 atmospheres, and it's decomposing into the elements in their molecular forms. And in this case, I do see a 2 to 2 to 1 ratio. So I'm looking at this quickly and I'm saying, hey, nothing's out of equilibrium, so it's going to be that squared times that over that squared, right? And what do they tell us when we come to equilibrium? Sulfur is at 0.02. Well, initially it's nothing. So I'm thinking to myself, that's going to go up by 0.02. That must go up by 0.04. Do you see that? For every one of those that forms, two of those that forms. So on the top, I've got 0.02 times 0.04 squared, which I can't do in my head. And in the bottom, it's going to be that number squared. That's our H2S. Well, I guess that goes down by 0.04, since two of those must go away for every one of those that is formed. And that's going to be 9.96 since it started at 10, but it gets squared. Oh boy, I better work it all out. But I think I could write down the numbers and do it at this stage. So if you like that, just do it that way. Most students like ice tables. Almost all teachers insist on ice tables. I don't think you need to really, but write your balanced chemical equation. Write down those initial conditions that they gave you. That's it, H2S. Nothing's happened yet when it's initial, but the change, well, they don't give you that either, but the product, one of the products goes up to 0.02, so the change is clearly plus 0.02. This has to be plus 0.04. That must be minus 0.04. Completing the ledger, writing the balance, the equilibrium expression. Don't forget the square stuff. And then just now whip out your calculator, plug that in, and we have an equilibrium constant of 3.2 times 10 to the minus 7. Notice we call it K sub B since we're dealing with pressures. As we pointed out before, gas pressures are analogous to molarities. They really are concentrations, right? And that is an incredibly bad equilibrium constant. And you know what's interesting to consider is that if you don't want this stuff to decompose, well, you want the equilibrium constant to be very low. So maybe it would take quite some time for this stuff to decompose appreciably. Although I have to point out that it's dangerous to assume that there's direct correlation between rate and equilibrium. Okay, this is an introduction to solving equilibrium problems.